Let's start. Hi, everyone. Welcome to today's webinar. And it's my great pleasure to introduce our speaker, Dr. Weijie Su. Dr. Su is an associate professor in the Wharton Statistics and Data Science Department at the University of Pennsylvania, and with additional appointment in computer and information science and mathematics. So Dr. Su's research focuses on statistical foundations of generative AI, privacy-preserving data analytics, high-dimensional statistics, and optimization areas that are highly relevant to today's rapidly evolving data science landscape. And Dr. Su also has received several awards, including the NSF Career Award, and he's also the recipient of the COPSS President's Award this year. So please join me in welcoming Dr. Weijie Su.
Thank you for the invitation and also for the very kind introduction. It's my great pleasure to give a talk at the Inforum's DMS webinar. So this piece of research is mostly about alignment for LLMs. And so the story begins with the octopus. So the octopus is living under the sea and has no knowledge about human language at all, but it has access to the human's conversation through the fibers. And so the question is that can the octopus finally understand human's language and by listening to our conversations for a long time. So this is essentially the idea, the original idea of next token prediction. Because next token prediction essentially is to ask, given the previous text, can you guess what is the next word? If you understand what is the next word, basically you understand human language, at least according to what Ilya Sutskever suggested. So when this was first introduced by Ilya Sutskever and his OpenAI colleagues, it was 8 years ago, and very few people trusted this idea. But now, so this is basically the foundation of all these language models. And so these language models has a basically has a black box nature. But we argue that this is actually a blessing for us, for the data scientists working on data science, basically. So this essentially relates to the bit lesson in AI, a very influential article by Richard Sutton, who got the Turing Award last year. So he argues that what is most important in AI is essentially the scale of the system and how can you leverage more computation, how can you incorporate more data. And the hard-coded knowledge tricks actually in the long run are not going to work. So based on this idea, so essentially what we need to do, essentially we don't need to deal with perhaps the internal mechanisms of these neural networks, whether it's transformer, whether this is LSTM, and this is usually less of a big issue. The most important part is that language model essentially is a blurry image of the whole web. It's a compression of the data. So the data is from the web, has already some certain structure. And can we incorporate and inherit this structure during this compression? So that's the question for example, every data scientist can try to answer. Okay, so this essentially seems to me as an opportunity for us working on operation research and statistics. So I actually wrote a position paper to express this idea, and so the position paper. So in this position paper, I argue that the language model basically has two properties. First, as we said before, is really a black box nature, it's a black box. And the second is really data-driven, data-centric. And these two characteristics together ensure that language models actually is precisely something we data scientists, okay, who work on operating research and statistics are good at. Okay, we only need to model the input and output. We don't need to deal with the internal mechanism, actually, at least for many applications. So based on this idea, so we suggest lots of research directions where we people working a little bit theoretically inclined can do difference, including alignment, uncertainty quantification, and how to deal with hallucination and watermarking and evaluation. So this talk will be mostly be about alignment. So this is a joint work with many wonderful collaborators, and in particular, so the lead author is Jianchong Xiao. So he currently is a postdoc with me and co-invited with by me and my colleague Qilo. So Jianchong recently got an offer from National University of Singapore. So he will join NUS later this year. So so we all know that human preferences are diverse. So this is essentially so based on different background, right? Different background and different education level and all a different ethnic background. So we all have different preferences, right? And many prompts about language models actually are also about opinions instead of fact, right? For example, whether it's tea or coffee. So there's a no unique answer. So it's really based on your own preference. So then, even by looking at the original training data for ChatGPT, so a paper published by OpenAI like 4 years ago shows that even among these human laborers, okay, these professional human laborers, so about one third of the time actually they didn't agree with each other. Okay, so this is because many questions about do you like coffee or tea, right? Do you like football and basketball? And so there's no unique fact about this, right? It's mainly about it's an opinion instead of a fact. So based on this idea, so basically we need to fine-tune the language model basically to align the preference with the human beings. So this is done by this reinforced learning from human feedback in short RLHF. So this consists of three parts, and so we will focus on the last two parts, which I believe are more important. The first part is a demonstration of data, demonstration of supervised fine-tuning. So basically, you present language models with several examples of such a question and a good answer, and let language model to get familiar with what a good answer should look like. And the second step is basically to train a reward model. So the reward model is basically to train a neural network trained on pairwise comparison or ranking data from a human labeler. So language model will generate like 6 or 7 different answers to the same question, and the human labeler will rank the responses, tell me which is the best answer, which is the worst answer. And then we feed a language model, basically use the Bradley-Terry distribution, Bradley-Terry model and to tell which is to predict basically which is a good answer, which is a bad answer given a prompt, given a question. And the last, once you have a reward model, the reward model basically can tell you whether the answer is good or not. And then we fine tune the language model using PPO or something else. Basically try to ensure that the language model will try to output a response to maximize, okay, to maximize the expected reward as much as possible. So in a formal language, so first the supervised fine-tuning, the first step is basically try to try to maximize the likelihood, okay, based on given the question and maximize the likelihood of the answer. And the second step is train a reward model, and the train a reward model basically to maximize the likelihood for the Bradley distribution. So here, so this is the likelihood, and the sigma here is the logit, and the R is the reward. And last, we want to do a reinforced learning, try to maximize the expected reward as much as possible. Okay, so now let's go to the original two steps, step two and step three. So roughly speaking, step two, let's make a analog. Step two is basically that we want to find a good teacher. A good teacher basically can tell me which is good answer, which is a bad answer. Okay, a good teacher. And step three is basically such a analog analogy. So the teacher is given, so there's a reward model, and now we want to fine-tune the language model, and such that the language model on average will output a answer which the teacher thinks is good. Okay, for example, to make the teacher happy. So this is what the language model tries to do through fine-tuning. Basically, try to transfer the preference from the teacher to the student. Okay, so now let's first examine step three. So we are asking whether step three is this statistically good? are there any potential bias because of step three, why we want to transfer the preference from the teacher to the student? Ideally, we hope that after transfer, the student preference will be the same as the teacher's. But now let's see whether this is the case. Okay. So first of all, let's do some very simple experiments with Llama 7B and so a very small language model. But we already see that there's something potentially not good, and looks like the transfer from the teacher to the LM to a language model is not what we expect. So this is basically an apple and versus orange question. Okay, given a prompt or a question X, so there are potential two answers, Y and Y prime. Okay, we can think Y as apple, Y prime as orange. And now let's ask both the LMs and the reward model. Compare between the Y and the Y prime. What's your preference? What's the probability that you prefer Y versus instead of Y prime? So for the LMs, for the reward model, actually the probability actually is quite smooth. Actually, of course, there are more density near 0 and 1. Okay, but there's a quite dense probability distribution between 0 and 1. Okay, you see there's a density right between 0 and 1. But look at the LM, which is basically the student after fine tuning. So the preference for Y versus Y prime is either 0 or 1. So you see all the probability densities are supported either near 0 or near 1. Okay, so this means that the teacher actually is quite diverse in terms of her preference. She prefer the thing continuously from 0 to 1. But for the student, after fine-tuning, the student actually becomes quite stubborn, prefer apple either with probability 0 or 100%. Okay, so there is no middle ground, roughly speaking. Of course, this is an extreme case, but there's such a significant difference between these two. So we call this basically preference collapse. Roughly speaking, for the teacher prefer apple with probability 60% and 40% for orange. Okay, teacher learns the preference, for example, from the human population. But after fine tuning, so the LM's preference actually is basically either becomes a one hot vector. So basically 100% either on apple or orange, and 0% for the other choice, for the alternative. So we call it preference collapse. So the code actually is easy to see, right? Because here we want to maximize the reward, and then suppose at this moment we do not impose any regularization. So basically we want to maximize the reward, and so the reward is a function of X is a question and the Y is the response. So the response is sampled from a policy distribution, which is a probability distribution conditional on the question X. And of course, it also depends on the parameters. So here, since we want to maximize the reward, right? So suppose there's apple and orange. Although apple's probability is only 51%, slightly higher than orange. But since we want to maximize the reward without any risk, so in this case, suppose there's no risk neutral. And then we want to basically maximize, we want to put 100% all in apple and 0% on orange. So in this case, basically the majority becomes 100%. The minority actually becomes 0%, actually becomes none. Okay, so this actually was already empirically identified by this paper. People found that actually, although in the training data, for the reward model, the imbalance actually is tiny. For example, just between 51% and 49%. But after fine-tuning, the majority becomes much more advantaged. Could be boosted from 51% to 60%, 70%, even higher. So we call it, so this is essentially the phenomenon of preference collapse. Of course, OpenAI has all the smart people. They already identified this issue. So I attended a keynote talk by John Schumann, who was a co-founder of OpenAI. So like 3 years ago in Hawaii at ISML. So basically, they listed a bunch of similar issues. Basically, they observe when they train language model. So the language model basically has a strong preference about certain patterns, which actually the human do not express such a strong preference. But they basically call it over optimization. And their solution actually is simple, just to do not chain for long. Early stop, okay, early stop. But this is certainly not a it's a pragmatic approach solution, but it's not a completely does not completely solve the bias issue, right? Because if you stop in the middle, your bias could be 50 half larger of the original bias, but it's still there. It's still not it's not there, right? So our so basically, we hope that it's possible that we can come up an approach such that the preference between human, the reward model, and the LMs could be exactly the same, at least from theory. Can we do this? Okay, we want to match the original preference, 60% for orange and 40% for apple, and then after fine tuning, it will still be 60% versus 40%, identically. There's no difference. So this is what we want to achieve. So roughly speaking, we give this property, we name this property preference matching. We hope that the preference actually will be basically the same as the original probability distribution among different responses, all right? Earlier on, we only talked about two possible alternatives, apple and orange. But in general, two can be any, right? Can be n. And we hope that the preference probability after fine-tuning between yi and yj will basically be the same as the original preference from the reward model, pi and pj. Okay, preference matching. So what we want to do is essentially we want to impose a regularization term to the original reward. So now essentially we have a adjusted reward r of x and y. X is again is a question and y is an answer or response. And the regularization is basically a univariate function. It's a scalar. And so it takes as input the probability mass function of all different possible responses, y. And we want to hopefully find such R. So now let me just first present the theorem. So the theorem says that, yes, there's such a preference matching regularization term, and it's if and only if. So this regularization term to R must be looked at be as follows. So basically, it is minus negative log of the probability mass function pi. Pi basically is the probability mass function for generating y, and plus two terms. This is a constant, which doesn't matter, and this factor actually will appear in integration by part. Okay, so instead, if we do not regularize, or we regularize only using a KL divergence with the original approach by OpenAI with a inappropriate coefficient, and in general, they will not lead to preference matching. Okay. So now let me briefly, the proof actually is simple. Let's briefly prove this theorem. So essentially, so we assume that there are n different responses, right? Y1 to yn. And so the associated original probability and the target probability given by the reward model is pi I for each response yi. And so we hope that, so the solution, so this is our target, right? And the target pi I is given by this bilateral distribution. And we hope that the maximizer of the adjusted reward will basically be the same as this target probability distribution. But we are maximizing, we are obtaining these probabilities through this optimization program, right? For this optimization program, the Lagrangian look like this. So this is the expected reward, and so this is a constraint. So the constraint that all these probabilities should sum up to 1. And so this is Lagrangian, and that must satisfy these first order conditions. And this first order condition should be satisfied for any I, for any reward, because pi 1 to pi n, they are all these free variables in this Lagrangian. Okay? So this means that this should be a constant because lambda does not depend on I, right? So since pi I star and the original probability, the title probability will be basically proportional to exponentiate the reward. So basically what we can show is that the regularization function must satisfy this equation. Okay, satisfy this equation. And this constant can depend on x, can depend on the prompt, but it should not depend on pi. And this essentially just gives and we can, for example, further differentiate on both sides. We get this basically differential equation. It's a very simple ordinary differential, second order differential equation. And the solution actually just takes this form. Okay? So essentially, this is the proof of this theorem. So now let me elaborate on this theorem. So basically here, so this is a reward. If we only want to maximize the reward, since there's no risk, right? And if you train a long time, so basically you are all in the response Y has the highest reward. And let's say Apple, and then Apple's probability will be 100%. But here we also say that we also want to maximize this thing. This thing actually is essentially after expectation, it becomes entropy, right? If you want to maximize entropy and then you want to be more diverse and you want to make your portfolio more include everything, right? Include everything. So then you won't be a collapse. You will be more diverse, including all possible different responses. So these two different directions actually will strike the right balance, and ultimately it will achieve the original distribution given by the Bradley-Terry distribution. So here, the first term actually C as a constant can be chosen arbitrarily, but for numerical stability, we can choose pi to this to be essentially minus log pi. So this essentially try to excuse me here. We can make this term essentially negative of this thing. So hopefully this whole term will on average will be close to zero. So that's why. So this is to ensure that this term is numerically speaking is neither too large or too small, just to ensure numerical stability. Okay. And C, this second term actually can be either chosen to be zero or maybe possibly proportional to pi. So we can also elaborate on this through this robust optimization perspective. So the dual, so the optimization program for this preference matching RLHF actually has a dual. So this dual actually takes this form, and the constraint is through this log sum exponential function. So basically, we want to find R reward such that the worst case are R prime, as long as R prime is close to R in terms of this log sum exponential function. It's not too far from R. And then we assume that this is the worst case. Okay, worst case means that I only observe R, but the truth could be is nearby. And then I want to basically protect myself in the worst case. I want to maximize the worst case. The worst case is where R prime is minimized. Okay, it's minimized. So basically, this is the robust optimization formulation. So this essentially says that so this preference matching optimization is basically not only to maximize R only, it's trying to maximize R, but in a worst case, in the bore specified by the log sum exponential function, and in this bore, and I want to maximize the worst case. And in practice, we also have to introduce some kind of truncation. Alpha is small, and we would only incorporate this regularization term when this probability output probability for Y is not too small. Otherwise, actually, we did it because mostly it's an engineering motivation. Because otherwise, the output could be just something which actually semantically means nothing. It's just something doesn't mean anything. It's not human. It's not natural text, and so that's why we need to have a truncation. And so the pi, the probability mass function, should be larger than some threshold. Let's say alpha. Okay, so this is our approach, and we hopefully so train after pre-training on all the language model, and also after RLHF, we hope that we would do a preference matching RLHF to match the preference with the teacher through this regularization term. Okay. So we did some experiments on Llama 7B, and so this is what we our experiment. So here the bar, the height is the divergence, is a KL divergence between the LM and the reward model's preference. So this divergence, if they have exactly the same preference distribution between LM and the reward model, and then this divergence will be zero, right? Of course, this is, in practice we don't observe such result. So what we observe that using certain parameter alpha, we can basically reduce the divergence between the LM and the reward model from the original approach by OpenAI using KL divergence. Reduce this by, let's say, like 20% or 30%. And so we believe that if we get a even larger language model, a better language model, we can further reduce the divergence. And but of course at this moment we don't have enough computation to accommodate such need. And but currently we can reduce the divergence by, like, let's say 20 to 30%. So this is the accuracy, prediction accuracy, validation accuracy on some benchmark, okay, on some benchmark data set. So roughly speaking, we are saying that using this preference matching policy regularization and the fine-tuned language model will still maintain basically the original accuracy as the original model. So this means that adding this preference matching as a layer does not compromise accuracy. Okay, so here our approach is this one, is the preference matching, the last one. So you see the preference, the probability, the accuracy probability is basically on par with the other approaches, sometimes even higher, like this. Is even the highest. Okay, so next, let's move on to this part. So we are asking, so far we have examined step 3, right? Step 3 is basically to say that suppose teacher's preference is the target, it's the oracle, and can we match the teacher's preference 100%? So basically we say that we cannot in general, but only if but we can do it by adding a regularization term. But now let's ask one step more. So we are asking in step 2 whether the teacher actually is a good teacher or not. So basically, the teacher is tuned, it's learned by fitting the language model to the budgetary distribution using this pairwise comparison data, right? Using the ranking data from the human labor. So we are asking whether these these rankings together will basically will give us a reward model which can really represent the preference of the population or the human laborers collectively. Okay. So this is our question, okay? And so now let's look at the budgetary reward model. So we assume that there are n different possible responses, okay? And y1 to yn. And suppose there are m human laborers, m human laborers. Each laborer will basically tell me a ranking of these different responses, and which is the best response, which is the second best, and which is the worst. And to make it simpler, we assume that there's no ties. So every human laborer will basically tell me which is better than the other. So the human laborer will not tell me that they are equally good. Okay, so basically we assume there's no ties, and the probability that yi is preferred over yj is either strictly larger than 50% or strictly smaller. So here we consider this definition, reward consistent preference. So we assume that for any two different responses, so the reward is consistent with the probability if the reward is higher for y compared to y prime, and then y will be preferred over y prime, meaning that there will be 51%, for example, more than half percent, more than half probability, more than 50% probability will be given to y as opposed to y prime. Okay. So this is actually an addition of the budgetary distribution. Because budgetary distribution, of course, satisfies this condition, right? Because P is basically proportional to exponentiate the reward. If the reward is high, the probability, of course, will be higher. But this is a transition of the budgetary distribution because you can use any other function, any monotone increasing function to transform from the reward to the probability, right? It's not necessary to use the exponential function. But however, this reward, so this reward function perspective actually will lead to, actually will contradict with the Condorcet paradox. So Condorcet was a French mathematician or philosopher 200 years ago, more than 200 years ago. He already is observed a well-known paradox, as saying that as long as there are at least three different responses, okay, three different possible candidates for the for president or for the mayor, like let's say Y1, Y2, Y3, and then in general there is no like universal winner, so there could be some Condorcet cycles. So this is the simplest example of such a Condorcet cycle. So for the first voter, A prefers Y1 the most, Y2 second, Y3 is the last. Okay. For B, it's Y2, Y3, and Y1. For C, it's Y3 and Y1, Y2. And then we can easily see that between Y1 and Y2, and the Y1 is the winner because two actually prefer Y1, only one prefers Y2, okay, so on and so forth. So this essentially gives us a very minimum Condorcet cycle. So Y1 is a winner to Y2 compared to Y2, and the Y2 is a winner compared to Y3, and the Y3 is a winner compared to Y1, okay? So in this case, so this is cycle, so there's no clear winner. Okay. So of course, this is well-known result. It's already known, but our question is more quantitative. So we are asking whether how likely the Condorcet cycles will appear. If so, and how can we get remedy? Okay, so that's our question. So for this, of course, we need to assume some probabilistic model, right? And to make the problem more concrete. So we assume that there's a probability model. We assume that for each prompt, and there are n different answers, y1 to yn. And a human labeler actually will express her preference as a ranking of y1 to yn. So basically, a human labeler will tell me a ranking uniformly random among all possible n factorial different responses. Okay. So this is, of course, a very simple model, but a model which is concrete and widely used in social choice theory. So, for example, Y1 for the first individual, the first human labor, maybe her preference is that Yn is the best, Yn minus 1 is the second best, and the Y1 is the worst. Okay, just tell me a ranking. Okay, tell me a ranking. So this is a well assumed, a widely accepted assumption used in social choice theory. Okay. And later we will basically extend it to non-uniform settings. And so with the probability, 30 probability, and so the ranking, it will become a mixture between uniform random rankings and any possible other rankings. Okay, so this is our first main result. So basically, we are saying that the probability of a Condorcet cycle actually is very close to 1. It's exponentially close to 1. And the difference is only merely is reciprocal to the exponential of the number of different responses. And so this shows that as long as n is large, which is typically the case, right? The language model can output many different possible responses. In this case, this probability this will be very small. It will be exponentially small. So this means that the probability of a Condorcet cycle appears is exponentially close to 1. Okay. So once this probability is exponentially close to 1, actually we can further, actually it's just a query. We can prove that the number of Condorcet cycles actually is exponential, can be very large. So this shows that fundamentally, Condorcet cycle is not a pathological phenomenon. Actually, it's a pervasive, it's a universal phenomenon instead. And the Condorcet cycle basically always exists in practice in general. So this shows that in general, if you want to use the reward model to represent human preferences, so fundamentally there's a loss, there's an approximation error. We cannot fully represent human preference using reward model only. Okay. So then how can we so next, so looks like we cannot only use the reward model, right? Is there any remedy we can use? For this, empirically, people have proposed this. So this is this is called the Nash learning from human feedback, proposed by people from Google DeepMind. So it's empirical, but the idea is very simple. And so basically, for the reward model, we want to represent preference using scalar, right? Every response, for every response, you have a reward. And then your probability is basically exponentially the reward and after normalization. So basically, if you have n different responses, the complexity of representative preferences is n, is a linear in n. But now for the natural learning from human feedback approach is basically to model the preference between y and y prime to apple and orange through a game. So basically, it's a game theory. It's a game between y and y prime. And so essentially, I want to parameterize the preference between y and y prime and different responses using basically n square, or at least n square over 2. Basically, n square such different parameters. So of course, in this case, it's more informative, right? So basically, it's more expressive. I can express any possible preference probabilities between any pair y and y prime. But the price we pay is that now the complexity is n squared instead of n is larger. So to really learn the probability, so what they propose is essentially to do a minimax game. So in this minimax game, so basically you have two identical language models, y pi and pi prime, they are identical. And so basically each want to beat the other. So for pi, and they want to maximize the probability that pi it is the winner over pi prime. And the pi prime wants to minimize the probability that this is the loser. It is a loser. So because this is a probability that pi prime is a loser. So this is essentially a zero-sum game. Okay. So for this zero-sum game, of course, in terms of to represent all possible response preferences, it's no problem at all to represent any preferences, even there are Condorcet cycles. But now the question is that for game theory, for games, right? It's very possible that the final Nash equilibrium will be a pure strategy. A pure strategy means that the final output optimal strategy for both pi and pi prime is to give a deterministic output, let's say y, deterministic. But this is not good, right? This means that the output from the language model basically will always be the same. Okay, if I ask a language model, could you please recommend a good restaurant in Philadelphia? And the language model will always give me the same answer. So, and then this will certainly lead to some diversity issue, right? It will lead to fairness issue. And then we want to incorporate study this phenomenon. And first, we introduce a concept called the Condorcet winning response. So in the literature, this is also called, for example, outright winner and there are other names. So it's very simple. Definition is very simple. A Condorcet winning response is just some response y prime, such that it is between y prime and any alternative y. Y prime is always y star is always the winner. Okay, there are always more than half of the population prefer y star compared over any alternative. Okay, so the probability will always be larger than 50%. So basically, we have two simple conclusions. So uh, let's first look at the second result. Second result actually is very simple. It's basically saying that if there is such a Condorcet winning response, and then actually it's very trivial. The optimal strategy for both pi and pi prime is just to output y star, right? Because y star is basically the silver bullet. It's just the optimal strategy, right? No matter what which card you play, I should always give y star. But now let's look at the first conclusion, which is less trivial. So less trivial is that is a if only condition. Okay, so if there's a Condorcet winning response, and in this case, of course, this will be pure strategy. But if doesn't exist a Condorcet winning response, and in this case, the optimal solution to this the Nash equilibrium of this game theory of this game will always be a mixed strategy, meaning that the language model pi will always output at least two different responses. Okay, y and y prime, always at least two. So this somehow at least preserve the diversity to some extent. Okay, so for this actually, what we do actually, by chance, we also resolve several open conjectures in the field of in the field of social choice theory. For example, in the social choice theory, they already observed that the probability of consensus cycle will converge to one, but their rate is suboptimal, and our exponential bound, for example, this one is basically optimal. Okay, it's optimal. It's optimal compared to the literature. Okay. So now, so we basically have identified the if and only if condition for the Nash learning from human feedback to have at least two different output in the Nash equilibrium. And that question is again as early on. What's the probability of a Condorcet winning response? Okay, so we can bound this probability in this expression. So when n is fixed, the number of human laborers is fixed, but the number of different responses is very large. And then among these three terms, and the middle term, this term is dominant. Okay, so roughly speaking, the probability in this asymptotic region, and the probability that a Condorcet winning response exists is okay, and it's basically no larger than this term. Okay, no larger than this term. But now we also have a lower bound. So the lower bound is saying that basically in the same regime, the probability of a Condorcet winning response is lower bounded by this term. And look at this term, that term. Basically, they're the same. The only difference that here there's some logarithmic factor. But if you look at the exponent of n, you see that suppose n is very large, it's a dominant number value here. And the exponent of n here is basically here, this is 1, this is minus m over L. So this is essentially 1 minus m over L. Look, so they match, right? Match. So this means that so this here, the upper and the lower bounds, basically they match up to some logarithmic factors. So that's why we basically have a sharp characterization of the probability of a Condorcet winning response. It's basically n to the power 1 minus m over L. So L is what? L is basically the half of n, but taking the seeding function. So this means that if m is a even number, so this is half of n. But if m is an odd number, so this is m plus 1 over 2. So basically the exponent look like this, and as the number of voters increases, and you see, so this exponent easily approach to 1, okay? And it will be, of course, it's negative, so it will be close to 1. So basically, we show that in the case where m is very large, and so the Condorcet winning response actually the probability is very small. It's basically of the order 1 over n. Okay, so the reciprocal of n. So if the number of response is large, and then this probability is very large. It's very small. It's tiny. So in practice, we basically would observe a Condorcet winning response if you have a very large number of n. The ranking is very long, for example. Okay. So now we further examine a extension of this Nash equilibrium. Okay, because essentially we want to ask this question. So far, even there's no Condorcet winning response, and what we can say is that the optimal Nash equilibrium is a mixed strategy. Okay, to output at least two different responses. But suppose that the true distribution, the target distribution is given by this brother target distribution. It's basically exponentiates the reward and normalize. So this means that suppose that the probability distribution in truth, okay, in the ground truth is given by this brother target distribution. It's given by reward model. And then can this Nash learning from human feedback recover the original planetary distribution? Can it? So in general, so we say we can actually from proof in general we cannot. But now let's consider an extension. So this extension is basically to apply a function, to apply a transformation of this probability. Okay, so phi is a function which we will determine later. So we hope that after you transform this probability, and now let's play again. It's still a zero-sum game between pi and pi prime. So now pi wants to maximize the probability transformed by this function phi. And y prime want to minimize the failure probability transformed by phi. Okay, the same function. Of course, phi here should be a monotone increasing function. And look, so the original NLHF, Nash learning from human feedback, is just the case where the phi function is the identity. And so the RLHF, if we force it to be in the game theoretical setting, and then this phi essentially is just log of t over 1 minus t. Okay, essentially the likelihood, the likelihood using the logit function. Okay, so now the question that can we find a possible choice of phi such that the ultimate solution to this natural learning from human feedback is good, and how good it can be, especially when the reward model is true. Okay, so there are several desiderata. The first desiderata is that if there are condensate winning response, and then we should output the winning response, right? Because this is the number one. And if there's no such winning response, and we hope that the optimal strategy should be mixed, output at least two different responses. And moreover, if there's a Smith set. So Smith set is defined as the minimum subset such that any element in this subset is a winner compared to any outside response, any response outside of this set. Okay, so this means there could be a cycle, right? It's a small cycle, and A, B, C, D, A, B, C, A is a winner compared to B, B is a winner compared to C, C is a winner compared to A, but all the other responses, let's say D, E, F, G, all the others, so they are loser compared to A, B, C. So in this case, actually, we can prove that so there's a very clean mathematical characterization of the phi function for each of the derivative. For the Condorcet consistency, we can prove that this consistency will be satisfied, meaning that if there's a winner, and then we will output the winner. In this case, phi should satisfy this condition. Phi t should be larger than phi at half, okay, and versus t should be smaller than half when t is smaller than half. So you see, and so this is when, so that's why the natural learning from human feedback satisfies this condition, right? Because this is a case where phi is the identity. So if phi is the identity, of course, this condition is satisfied. For the mixed strategy, and just to satisfy this, and again, if phi is the identity, and then this is also satisfied. For the Smith consistency, we have this, and again, if phi is the identity, we also have this condition satisfied. But in general, and for this, actually, we kind of have good promising results, right? So this shows that we can actually choose a non-identity function to satisfy all this. Okay, identity function is only the special case. But if we really want to recover the original distribution, if the original distribution is given by the Bradley-Terry distribution, okay, if there's no cycles and the original reward is basically just given by the Bradley-Terry distribution using some rewards. In this case, is it possible to find a general phi such that the optimal solution to this Nash game, okay, will basically will be the same as the Bradley-Terry distribution. So this is an impossibility result. The answer is no. Okay, answer is no. So this shows that in general we cannot find a phi function, and such that by playing this game between pi and pi prime, we can recover the reward model if the truth is given by the reward model. We cannot. So this is a little bit disappointing. Okay, disappointing. So this basically shows that game theoretical alignment it's possible to first it has an advantage to express any possible preferences, including the case when there are Condorcet cycles. It can also output a mixed strategy, preserve certain level of diversity when there are no winning response. But in general, it cannot give the exact reward distribution, even when the reward model is true. We cannot. Okay, so basically this is our summary. So the summary is saying that in general there's a cycles. Okay, but if you are really in the case where there are no cycles, and then we can use the reward model to represent the preferences. And if you use the Brightly distribution and then the Brightly model, and then to collapse to the winning response. And so if there's no cycles, okay, if there are cycles in general, which actually appears with probability almost one. In this case, for example, if we use the natural learning from human feedback, and so depending on whether there's a winning response or not, if there's a winning response, in this case, we will still collapse to the winning response. But if there's no winning response, in this case, we will at least we will output at least two different responses, preserve certain level of diversity. Okay. So last, so we want to get a hand on how well I can approximate the true distribution when there are condensate cycles using the reward model only. So we already have seen that if there are condensate cycles, we cannot use the reward model to fully represent the probability distribution, right? So it's impossible. But now we ask a more quantitative question. Yes, I cannot fully represent the preferences using reward model, but maybe it's close, right? Maybe it's close. And what's the gap? And can we get the gap in a quantitative way? So then we have to use this scale divergence. So basically, we want to use this underlying distribution P. So P is not given by reward model. So they are already cycles. But now we just pretend that we are still using the reward model to represent the preferences. And now we want to find the minimum, basically the projection. The projection of my current probability distribution, the current distribution to the distribution parameterized by the reward model. Okay, the projection. Why do we use scale divergence? Because scale divergence has the property that if there's a model misspecification, then essentially the gap essentially is mapped by the true distribution, the true parameter projected to the set you maximize over for this maximum likelihood estimation through this scale divergence, right? So if this scale divergence is large, and then this means that the gap between my true distribution and the rewarded distribution actually is large. Otherwise, it's small. And basically, we identify a value which basically can capture the fundamental gap. So this gap essentially is as follows. So first, for any probability, let's stand it at half. Okay. And now let's consider so this B matrix. So B matrix essentially is just like the pairwise difference between any coordinates. Okay. So you see, and now let's consider, say it's the image of B, and say, so image of B, essentially this is the any possible expression, any possible probability distribution can be represented by a reward, right? Because R is essentially reward. The difference is the exponentially the difference essentially give me the difference, the probability between preference probability between I and J. So this is the complement. So complement essentially is the space where I cannot represent the preference using reward model. Okay, so this is orthogonal to the image of the B matrix. So what we can prove that the gap between the projection of the original the true distribution to the reward distribution essentially is the L2 norm of the residual probability projected to the complement of this image set. Okay, so if this projection of the projection this has a large length, this is large, meaning that then the approximation error is large. There's no way to easily use the reward distribution to represent the true preferences. Okay, so further we get a lower and upper bound for this value, and essentially if m is really large, so essentially in this case, for example, m is large enough, m is larger than log n in this case. So basically this is become a matching lower bound. So the bound is basically n squared over n. N squared over n is basically the lower matching bound if m is larger than log of n. Okay, so I think I stop here. Almost time is almost up. So basically, these are references, and thanks for your time.
Thank you a lot for this interesting webinar, Dr. Su. So next we will have the question and answer session. If the audience has any question, please feel free to type your question in the Q&A chat box. And also from the panelists, do you have any question for the Dr. Su?
Yeah. Any question? Welcome. Thank you.
Yeah, so hi, can you hear me?
Yes, Udi, we can
Yeah.
hear
Yeah.
you.
Please.
All right. Yeah, thanks so much for the great talk. Maybe I have one quick question. If I under- so I think for the first half of the presentation, I remember you mentioned that I really appreciate that you shared the perspective that whenever, even if you have a perfect river model, you might see there is a response collapse when you're using the reward model to fine-tune the LLM, to fine-tune the performance of the LLM. And so I think here there's a fundamental argument behind the scene that you basically assumes that the human preference, population-wise, has to be probabilistic. So maybe this is more like a philosophical question. I'm right now just thinking out loud. If you're looking at the one particular individual, maybe you can argue that this person's preference could be deterministic. The reason we're seeing the human preference is probabilistic is because we are looking at large body of population.
Mm.
That's where the variation comes from. But eventually, by the end of the day, the way how we interact with LLM is individualized, meaning for every single individual we talk to LLM, we're expecting to hear a deterministic answer given by the LLM system. So I wonder if there's any, do you think that could be interesting direction to explore by factor in the human, I don't know, maybe profile to identify or to, I don't know how to put this, but to realize or to review the uncertainty in a way that at individual level the preference could be individualized. I'm not sure if I explain myself clearly.
Oh, yeah, yeah. I think this is a great question. And here we essentially we consider the user as a population. So we want to language model to preserve their overall preference from the population.
Right.
And so for specific use cases, right? So if, for example, if the language model only for users from certain, for a company, for certain occupation, for certain type of users, or maybe a specific users, maybe we can know the preferences better. It's more refined. And
Mm,
but however, the methodology here is basically the same. And so basically, because we always model the preference through the reward model. So
mm,
the population actually is kind of a dummy thing. So we do not directly model the population preference only through the reward model. So
mm,
for a specific individual or a specific group of individuals, we can use the reward model to represent their preferences, for example. Yeah. But the difficulty, I guess, is that for a specific user, it's more difficult to understand the reward distribution for the user
sure. Because you
because
don't have the
the
data.
data
You
is
don't have
sparse.
enough
There's
data.
only one data
Right.
point, right? So
Right.
it's difficult, more difficult. Yeah.
So if I understand your point correctly, so basically your argument is it doesn't affect the methodology itself. You simply just learn the preferences conditioning on a specific user context. As long as you have the access to this user context, also you have access to a large amount of data points that can
Yes. Yeah.
well represent the human preference for this
Yeah.
context.
Exactly.
Right. Yeah. Thanks.
Thank you, Woody, and thank you for the answer, Dr. Su. Um, I didn't see the further answer in the chat, so I have one quick answer for the second project you present. So how can we know the conducive cyclic exists in the reward functional model? Like, is there any a way to determine or diagnose this cycle?
Uh, uh, so determine. So basically, and so if there's so and so this is actually a graph problem. I'm not sure if this is complexity. So the simplest way, for example, is just like pick any three or four larger nodes in the graph and look at if there's any cycles, right? And but of course, there are exponentially many such choices, right? If you want to examine all one by one, the competition is exponential. Cannot do it. So we can um, we can say that the control cycle exists if we find one, but it's hard to say that it doesn't exist, right? Unless you examine all possible such possible cycles. Yeah.